To have everybody's attention, today our speaker is going to be John Clement, and John is an expert in physics teaching. And like I could say, he's an expert because some of us, we teach physics to graduate students, and we don't really have to know how to teach as much because we have really interested students who they're already interested in the subject. He has the hard job where he has to teach students who he has to convince them to learn the material, and he also has to convince them what they're actually going to get out of it. So doing that takes a lot of talent, and so we're lucky enough to have John Clement here, and what he's going to be talking about is physics education, which, as you can see, it's an interesting area because it's not like traditional education in other fields, and at the same time it's much more than that, and it's something which, interestingly, I've seen, from what I've noticed, it's studied more in physics departments than it is in education departments. So I'll turn it over to John.
I'll give you the brief bio. I actually got interested in this back when I was considering what to do, and it was a choice between several alternatives, one of which was to possibly go to Vietnam. So I went to graduate school instead. A lot of people did that. Well, I eventually ended up with a high number in the lottery anyway, so it didn't matter. But I picked my graduate school on the basis of the fact that they were known for excellence in teaching, Rensselaer. And then when I was at Duke doing some teaching, I developed some techniques that I have later, many years later, found out are actually the sort of things that people in physics education are learning to do, and techniques that are now considered to be standard in the physics education field. One of the things I do want is I want everybody to be near somebody. So if you're off by yourself in a corner, I'd like you to either move up or move over, or because I want a little bit of discussion to go on. I want you to be able to talk to somebody. I don't want anybody completely isolated. And that's part of the deal in physics education, because you have to begin to get the students to talking to each other. Now, I have here some references. These are the only references I'm going to give you. They are probably very good sites to get started, to see information. If you don't write down anything now, that's just fine. A lot of what I'm saying will appear on these websites. The modeling one is the best one for teacher workshops, and it's a program that has been absolutely the most successful in terms of getting high school teachers to do a good job. The next one is Eric Mazur. He wrote a little book called Peer Instruction, and that's information about that and about his talks and everything are all on there. You can go through the talks. There's a wonderful video, if you can find it, which actually repeats some of the stuff that I'm saying. There's a free online journal. You just go to that website and you have a Journal of Physics Education, and it's edited by Joe Reddish at University of Maryland. And if you're not a member of the AAPT, I'll put in the plug. Join, because their journals are wonderful. They don't always have good articles on physics education research, but they do have some. All right. Now, these are results that should or should not be familiar to you. If you're not familiar with them, I will recapitulate them in a hurry. The last talk I gave, I talked about them a bit more. Richard Hake, in a 6,000 student survey, found that conventional teaching gain was a maximum of 25%. By this 25%, we're saying that the students learned a maximum of 25% of the stuff that they didn't already know. It's what's called a normalized gain. But in interactive engagement courses, you can get 30 to 70% gain. This figure has now been pushed up to 90%. There have been some classes like that. But he also did an indirect measurement where he looked at the scores of incoming students into a physics class in college, and he found out that the ones who had high school physics only had gain of 10% over those who didn't have high school physics. So from that, you might conclude that the average high school physics course has 10% gain, which is probably true of the average introductory college physics course. Okay, everybody loves to say that all students are worse now, but there's no evidence for that. We have no direct evidence for that. No way of even finding out if they're really worse. Because, of course, we weren't testing them back then. Now we are testing them.
Characterize what back then is?
Back then could be in the 1950s, 1960s. Name your favorite era where you think the students were better, and there's no evidence for it. We only have evidence from starting 1970s in physics. So, conventional learning paradigm. This is the one that everybody's familiar with: lecture, direct instruction. The whole idea is a lecturer transmits concepts to the students by talking about them, not about the students, of course, about the concepts. And one might call it a transmissivist paradigm. Well, what are some of the problems that you run into in communication theory? You would say, look, the lecturer has to get the information, he has to encode a message, the message travels over a medium, some sort, the learner receives the message, the learner decodes the message, and the learner stores the information. That's what we're talking about. And of course, problems can occur all the way around. Maybe the person didn't encode it properly. Maybe there's noise in transmission. If you're in a noisy room, obviously, it's going to be hard to hear a lecture. Improper decoding. The students might not decode it properly. Improper storage. Notice that this depends upon the learner having the same model for decoding as the lecturer uses encoding. That's what I would call one of the biggies. All right. Mazur. Eric Mazur, I just saw his talk on this, and I was familiar with these ideas. He asked the question, do students learn by being shown something? And I know you've always heard the thing, okay, tell me and I may learn a little, but show me I learn a lot more. So on a scale of 1 to 5, do students really learn by being shown? Is this a better method of teaching? I want you to all come up with a number, and then I want you all to vote on what you think the answer is. And we'll vote by the simple expedient of using digital voting. 1, 2, 3, 4, 5. Digital encoding, right? 5 digits we can encode easily. So, what do you think about it? Well, let's all vote. 3s, 2s, 5s, 1s. Okay. It looks like it's around a 3. Okay. Now, there's a common misconception, and that is that when you have, let's say, a couple of scales, and you have a beam going across it, you put a block on it, a lot of students tend to think that all that happens is the 2 scales are going to read the average weight. Each one will read half, no matter where you put the block. You can easily do a demonstration, and Eric Mazur, as an experiment, did precisely this sort of demonstration. He put the block in the middle, the 2 scales read this. He moves the block over, this scale reads this scale reads this. And he wanted to know whether or not the demonstration would dispel the misconception. So, 2 months later, he gave them a surprise quiz. Didn't announce it, just sort of a memory quiz. And the whole idea was he asked them what was the result of this demonstration. So how many students got it right? Okay. How many students got it right? And we'll get you to vote. 10%, 20, 30, 40, 50, 100%. I want you to come up with an answer in your own mind. How many got it right? Just a memory, what were the results? 100%, 100%, I see some 20%, some 50%, some 30, some, I don't know, it's probably, 40, somebody just voted 60. Okay. Here's the result. 18% got it right. So if you voted 20%, you were pretty darn close. 82% got it wrong. They still had the common misconception that the plank evens out the load even when the object is on one side. They were shown this directly.
And didn't remember it?
And they did not remember it. Absolutely did not remember it. The reason why Eric Mazur did this experiment is because he had heard that demonstrations were fairly ineffective. And by doing this, he proved it to himself. All right. One student actually went, and he had written right justifications. One student wrote, as demonstrated in lecture, both scales will read 10 newtons regardless of where the center of mass is located. The platform and the metal block form one unit that is being measured, so the scales show 2 evenly distributed readings no matter where the metal block is placed along the platform. Notice, he didn't really ask them about the demonstration. He just asked them the question, what would they read? And this student went so far as to say that he saw in the demonstration this result.
Now, that just amazes me. It really does.
All right. Well, yeah, I want you to come up with an answer. I want you to discuss with your neighbor, come up with an answer. Why do you think this is happening? What is going on with the demonstration? Come up with an answer. And we'll take a few answers from the gallery.
I've seen this before.
I've seen it happen.
You want to come up and join the discussions?
Yeah, I actually had a class where I gave out a quiz every single class. And when one day I would have a policy that I would answer any question and ask me. So the girl asked me a question, I worked out the problem on the board, completely gave the final answer to it. It turned out that was one of the quiz problems. So I raced off the board, handed them the quiz. And out of 20 people in the classroom, only like 3 or 4 actually got that problem right, even though it was multiple choice. The problem is, I think part of it's attention span, where if they're learning passively, they don't actually necessarily get a lot of this stuff until it's actually been convinced to them and they actually interact.
They have to see it on a gut level, not just a pictorial level.
Yeah.
Okay. We have some answers? Okay. I don't want to spend too much time having you discuss, but you see, that's one of the things that has to happen to have students learn, is they have to discuss things, they have to come up with their own ideas, and at this point, I will do what I'm supposed to do in Socratic dialogue, and I'm going to take any answers that people have, and I may go, okay, and I'm not going to tell you what the answer is until after you've gotten a few answers, right? Yeah, so somebody come up with an idea.
I think that you should have read what they actually thought it was rather than what.
Okay. Any others? Yeah?
I think that they had such a strong hold on their preconceived notions of the way the universe works that when they saw the data that conflicted with it, they misinterpreted it to confirm their prior model rather than changing the model based on the new data.
Okay. Any other?
I think also it has a little bit to do with their attention span when they're watching it, and a little bit to do with actually working it out versus seeing it. It's like passive learning versus active learning.
Okay. Yep.
I think a lot of students get overwhelmed with all the verbiage. They don't understand weight, they don't understand force, they don't understand Newton, they don't understand center of mass. Until they learn conceptually what all those things mean, then they're just parroting what you say.
Okay. These are all pretty good ideas. I'm going to give you the one that Mazur made, and this is the one that I think cognitive psychology also agrees with, is you interpret what you see according to your mental model. I think several people mentioned that. So what you remember is basically what your mental model tells you what happened, and not what actually happened. And I was in a discussion with somebody on a chat line who insisted that a lecturer said something, and I went and looked at his paper and found out he didn't say that. Well, but he said it in the lecture, and I go, but he didn't say it in the paper. And the point is, this person has a very strong mental model, a bias towards saying what he thought the person said. And so I question that. So how do you make demonstrations more effective? And rather than having you discuss it, maybe we'll just get a few ideas. Yes?
One thing is, it's when you see a demonstration, it's a lot like watching a magic trick. And so if you actually see somebody solve somebody in half, and you haven't actually looked at how the trick is performed, small kids actually believe that that's what happened. So I think that the only way to really make it more effective is to actually perform the trick and actually see how it works.
Very interesting. I'm not quite sure how I do that, but...
To me, I thought you were headed in the direction of doing a hands-on, so you have a lab. where you get the pieces and you put it together.
Well, of course, that might be a good thing to do, but we're talking specifically about, in this case, about lecture demonstrations, where somebody shows you, because sometimes you don't have the wherewithal or whatever you want to make the demonstration more effective. It's just the way the class is structured. You can't.
You just don't have the two scales and the block, concrete block, and the blank, or whatever.
So, yes?
What triggered my mind through this was a working meeting. Because in a working meeting, the objective is everybody contributes and you get a result coming out, and there's a document or something produced in a working meeting. But I know in a lecture you can't, but so you can approach that in a lecture in many ways by having the whole class with an objective of producing something that results from it.
Yeah.
I think before you move the mass to the over on top of the one scale, that you ask the students to project or give you an estimate as to what's going to happen when the weight is moved to one end.
Heather?
And then
Yep.
on top of that, after they see the results, ask them to explain why they think that their guess was wrong.
Okay. Okay. Here's the results of things. Now, Catherine Crouch did this experiment. She looked at it. She found one thing that made a big difference. It seemed to make a difference was predicting. Predicting ahead of time, it helped them to remember it. And a subsequent discussion afterwards to think about the misconception is very valuable. But Eric, and this is off of his recent talk, I don't know whether he's revised this or not, notice, by the way, with no demo, the number of right was 30. After a demo, the number of right was 18. Then you get him to predict, it goes to 29. You get him to discuss, it goes to 30. So that's a very interesting result. And he didn't comment on that, but having done a lot of reading and thinking about it, I've actually seen that sort of thing before. Essentially, the 30 to 70 was sheer guessing. Here they were thinking about it, and they started realizing, hitting their misconception. But at least they were thinking about it a bit. And here they're thinking more, and here they're thinking more. So even though it looks like you haven't made progress, what he did was he then took a series of problems that he gave them later and looked at how the students did the problems depending upon which treatment they got. So he had these problems which are actually tests of understanding. You know, they're very simple things. And with no demo, you had 31% correct. With those who observed, you had 42. Predictions were raised at the 41. Discussion raised at the 46. But when you start looking at other things along the way, you find that those who actually use torque, because if you're going to do this exactly, you've got to use torque as well as weight, the total weight. The point is, the number who actually did a better analysis went up dramatically, and the reasoning also went up dramatically, even though it may not be 100% correct. At least 85% were using reasoning. Here, what, 60?
Yeah.
60% were using reasoning? Okay, so what you see is that it actually had a beneficial effect, even though the immediate result may not have shown it. And I was very pleased a few people actually got it right. I hope I didn't give it away with my facial expressions. So now, how does memory work? Because that's an important idea. How does memory work? How do you remember things?
Now, not sure what you mean by that. You mean,
Okay, what do you actually store in your memory? For example, you see something and you store it, and this is one of the crux of one of the problems. How does your memory actually work inside? Come up with a model for memory. If you want to discuss it for a minute, that would be fine. I think we have a little time. Come up with some way of thinking about what you're actually storing in your memory.
even if the way it went on. So chemistry and neurological, I still don't understand them very well.
I think what he's talking about is what do you store exactly? Do you store sounds, pictures, processes, mentions? I mean, if you did, like if I look at the things I really remember, I tend to store like an actual process more than an actual store.
It depends on, sometimes when I'm doing something like physics, I will say store words, equations, sometimes, and mental pictures or physical pictures. And I try to link it to what else I've learned before that topic. If I have, see what can I connect it to that I already know.
Well, I don't tend to remember equations.
It depends. If I had to repeat it enough times, and it's important enough to me, like E times E squared, I can, not big equations, but simple little equations.
But I can, I mean, I'm actually better at deriving something or I'm not sure if the speakers are working.
It doesn't matter. There's no sound. No sound. Okay. Okay. Let's come up with some ideas. And I did mention the question, what are you actually storing when you store a memory? I mean, I think that's part of the crux of it. So let's come up with some ideas. I know you had some discussions.
You're turning on little neurons.
Okay. But you store pictures?
Images.
You store images.
Sounds.
Sounds?
Processes.
What?
Processes.
I seem, it depends on what I'm doing, what I'm learning, what I'm looking at. But sometimes I store a pictorial image. Sometimes I store numbers and graphs. Sometimes I'll store words or some combinations to them. And when I'm trying to learn something, try to remember something, I try to link it to something I already know about that topic.
Okay. Yes.
Go ahead.
Well, the reason why I said process is because for remembering physics equations, for example, I don't remember the equations as much as I can actually remember how the equations work together and what they actually mean. And if I'm storing music, like a song, I don't remember exactly the words to the song. I just kind of remember what should go with what. So if I can remember the beginning of the song, I can pretty much remember the entire thing.
Okay. Yeah. Any others?
That's interesting. Over to someone. Yeah, I guess somebody told me a long time ago, whenever you listen to a lecture, you try to apply it, something. So you try to find at least one thing you can apply, and you go do an action. You actually do it. You do the application. And I didn't hear anybody say they actually go do an action.
Okay. Well, I want to show you a little video. This is a very simple video. It was designed by cognitive scientists, and it shows somebody asking for directions from a stranger. The stranger is obviously, looks like a Cornell professor. It was done on the Cornell campus, being a Cornell graduate, but I mean, there's nothing there recognizable, Cornell, just shows some trees and grass and so forth. But there's no sound, but I want you to watch very carefully what happens. It's all been staged. The person they're asking directions from, the gray-haired person, has no idea what is going on. It's like candid camera. Okay, somebody comes up and asks directions, and I want you to, no, I don't want to do that. Play will resume at current position. How do I? We don't want to know that. What do we do? Yeah, I just want to get this play. Oh, there's the play button. Just press the play button. It's kind of fuzzy.
Oh, that's it substituted a different person. That's false.
Okay, well, they're going to replay. Okay, so we can go back to the presentation, which is right here. Okay, and from current slide. Okay, how does your memory work? Now, notice what happened in this case is the person, of course, is concentrating on just what's happening, the fact he's giving instructions, and he has no idea that the person has changed. No idea whatsoever. They've even done it with people with have deeper voices. By the way, if the person switches coveralls on, it turns out they're even less likely to be noticed because they're a working person, and the professor and the working person are from different realms of society, and so it turns out you tend not to notice people have been switched if they're from different parts of society. They even have one showing their shirt changes from red to blue, and the person still doesn't notice it. Yes?
Have they done that with people from different ethnic groups too?
I don't know whether they've done it with ethnic groups, but they did find that, for example, if the person was obviously of the same class as the person who was giving directions, that it would, you could do the switcheroo. Okay, so we gave an answer. Now, part of the answer is we only remember concepts and facts, but we don't remember photos. We don't remember playback sounds in our heads. Okay, we don't have enough storage for that. We remember a piece, an important piece of what we saw, and when you repicture it, you don't actually bring back the actual picture. You bring back the pieces that you have, and then you reconstruct the picture entirely. So when a student sees something in a lecture, and their mind doesn't agree with it, of course they store something completely different. And so when they bring it back, then they reconstruct the demonstration to be exactly what they think is going on. I happen to be very aware of this because I'm one of these people who has a great deal of difficulty with certain memorization things because I'm dyslexic. And I have to connect facts. I work entirely on ideas almost. A lot of things I just don't remember. So somebody says, oh, this happened. I go, yes. Lawyers are very well aware of this. They know how to manipulate people's memories and actually change them. It is possible to literally change your memories. And there's a famous experiment called what I call the blue shirt, red shirt one, is where the psychologist comes in wearing a blue shirt and he draws attention to it. The next day he comes in and says, well, color shirt was I wearing yesterday? And the students will say, blue shirt, okay. And then it gets, I want you to pretend you saw me in a red shirt. Just pretend you saw me in a red shirt. You know I wasn't. And then on Wednesday he gives them a test, what color shirt? And a significant fraction will check off red shirt, and they will swear that they saw him in a red shirt. Now, there's a reason for that, and it's very important, and that is that you have short and long-term memory, and your short-term memory, when you bring an idea up into your short-term memory, it's not really static. You can change that idea in your short-term memory, and then before the idea goes away, it gets stored back in long-term memory. It's a retrieve, put back cycle, almost like a computer. So that's one of the reasons why prediction works in demonstrations. If you have them predict and don't have too much of a time between the prediction and seeing the result, they can then store the idea back changed. And so their natural idea then is changed somewhat by prediction. There's a whole series of these called interactive lecture demonstrations, and I recommend them to you. With that name, you can find on the web. Okay, postpone. Remind me in 4 hours. Okay. So, transfer. This is always a big issue in terms of education. When you teach something, you want them to transfer it. So, for example, you have them do a problem. And you want them to be able to do problems that are different, but a little bit similar. And really what you'd like is to have them do problems that are completely different. So she did an experiment, and it turns out this is a classic experiment. She taught them the algorithm, the way of doing the problem, and then she also taught them the meaning of the problem. And then she gave them problems that were similar, but different. And the ones who were taught the algorithm got no transfer. The ones who got the meaning had near transfer. That's where you see where you're going to similar but different. So she went a step further than any of the people before had done. I have a copy of her paper, by the way. I don't know if I have it with me. Teach the meaning, then the algorithm, or she tried teaching the algorithm, then the meaning. And I want you to think about it. And which would work better? Teach the meaning, then the algorithm? Teach the algorithm, then the meaning? Or do they... Does neither of them work? So how we're going to vote on this is 3, teach the meaning and the algorithm. 4, teach the algorithm and the meaning. And give me a fist if you think neither of those work. I want you to think about it. Just get your own opinion. Now you can even discuss it if you really want to. I think this is more of an opinion poll at this point. So, you ready? Come on, give me a vote. Very interesting. You're voting almost exactly the way the mathematicians did at the last conference. And it turns out she was doing this with math. Almost exactly the same. Teach the meaning, then the algorithm. Now, this doesn't work. Only this works.
Interesting. That's something different. Now, my dad was a high school math teacher, and a very good one. And he, in his discussions with me at home, he always said, I always want to teach the students how first and then why. Because they'll understand why if they'll be in a better position to understand why if they've seen how.
Okay, why? Okay, how is algorithm then meaning, right?
Yeah.
Yeah, that doesn't work. It turns out that teaching the algorithm blocks the use of the meaning. And I've actually seen this. Algebra, it turns out, is a very easy way of getting students to solve a lot of problems. Okay, they have the problem, they get the numbers, they plug them into the equation, they crank out the answer, they've gotten the answer, and they have no idea what the meaning of that answer is. So one of the ways of doing this is, for example, in kinematics, you teach them how to do graphs, you teach them how to do motion maps, where they plot where the thing is each second, and then what you do is you go from there and you let them use that for solving problems, but you don't tell them how to solve the problem, you merely give them a technique for representing it, then you make them tell them to use these representations in solving problems, without telling them how to do it at all. That's what the modeling program does, and it does improve their ability to do problems. Now, there are some times when you do have to give them, a certain amount of machinery along the way. But in a lot of simple things, you've got to get them to invent the machinery, or they can't transfer it. They've just simply learned that one problem, they cannot move it to another one. Okay. This is a very, very recent article. It just came out in Science. I just got a copy of it over the web from a kind person, since I'm not a member of the AAS, and so it's February 2009. The experiment compares U.S. students who had, students in the U.S. when they go into a college class in physics, generally they may have had 1 year of physics. Sometimes they won't, sometimes they don't, so the average is probably, between half a year and 1.5 years, because some will have 2 years of physics, but that's probably atypical. Chinese students, on the other hand, have 5 years of rigorous physics. They teach them year after year, they build it up. And so, how much better did the Chinese score on the force concept inventory? I've already mentioned that. The force concept inventory is a test of understanding. It is not a test of the ability to do problems. Although obviously the Chinese students had some ability to do problems. And this test was all done coming into their first physics course in college. So, there might be other confounding factors. It's very hard to do these sort of things with every student. You can only do it with the students you have. So they tested incoming students in the US and they tested incoming students in China. So how much better did the Chinese students score on the FCI? And we'll do it by percentages, 10, 20, 30, 40, 50, 60, 70, 80. How much better do you think they did? It's just an opinion poll again.
The U.S. students doing better is not enough.
How much better did the Chinese students score on this test of reasoning, of understanding business? Well, 100% is not possible, because obviously the U.S. students had a score, and I think they scored around 50%. So the maximum is 50% better.
Okay, I think zero. See, when I say thinking 100, how much better, I'm talking about using the U.S. score as the base score.
Okay.
So that's possible to do.
Okay, that's possible to do. Okay. So, what do we think? 30, 20? Okay. You expect that they will go better. Sure. Here's the The U.S. students scored around 50%. The Chinese students scored around 86%. And this was after 5 years of intensive physics training. Now, you would think that maybe, and you can see the distribution of grades. I mean, they've tightened up. And this is just for the mechanics. There's also a similar graph for the electrical, but I'm not showing you that one. There's no sense. It looks the same. Just says electrical on the side. Okay? Well, one of the things that's always very important, you're pushing science and math by thinking about, well, look, it helps you to reason. Haven't you ever told students that? It helps you to reason, right? Okay, so I know you've all said that. So the question is how much better did the Chinese students score on a reasoning test? And before I have you vote on this, I want to explain the reasoning test. Reasoning test has a series of tasks. And if you want a copy of this, I can give you a copy right away. You'll have a copy. You can take all the notes you want. I don't care, but I want you to process a little bit more. It's a test invented by Anton Lawson at Arizona State. Actually, he took a test invented by an Englishman, and the Englishman took the questions on it from Piaget, who found that there were certain tasks that students could do at certain ages. Proportional reasoning, conservation reasoning. Conservation reasoning, there are 2 tests on that, and they should be able to do that before age 9. One of them is, if you flatten a ball of clay, does it weigh the same? I've seen high school seniors who still don't understand that one. Okay, another one that a lot of high school seniors actually still don't understand is if you drop 2 marbles of identical size but different mass, one made out of steel, one made out of glass, into identical graduated cylinders, and they sink, how high will the water rise? And a significant number of students will actually tell you that the water rises more for the heavier marble than for the lighter marble, even though they're the same sizes. They've done these labs and everything. Incoming college students, same thing. You see that they miss this one, okay? Proportional reasoning, you pour from a graduated cylinders where the graduations are different. So, for example, one reads 4, the other one reads 6. Say you pour the water from the one that reads 4 and the other one reads 6, and then you give them, if you put 10 into this one, what will this one read? And 75% of seniors will get that one wrong. 75% get it wrong. Okay? 2 variable reasoning, looking at simple situations where you have 2 different things going on. Can you separate them and predict which of the variables was important? Was light important? Was gravity important? When you get to statistical reasoning, which is important to understanding things like medical studies, you get 1% or less of graduating seniors understand that. And this is from what I've seen in terms of what other people have tested and also the testing I've done. So anyway, you use these tests to find out what the thinking level of your students are. And it really correlates also with IQ. But that's another thing. So anyway, using the Lawson classroom test of scientific reasoning, how much better did Chinese students score on a reasoning test, scientific reasoning test? It also has control of variables in it. This is a toughie. They did a lot better on physics. So they've obviously had the physics.
10%.
Oh, let's get about it. Yeah. We have the optimists and the pessimists, and it's around 20%, maybe 30%. Here's the graph, U.S. and China.
Almost indistinguishable.
Yeah. Okay. The U.S. students essentially came into their course with exactly the same reasoning skills as the Chinese students, despite the fact 5 years of intensive physics, and presumably it's similar in math. So whatever was going on in these physics and math courses did not improve their reasoning ability. 1 iota. And the other interesting thing is you think about this, Chinese schools, there aren't as many of them. They should be more selective. And that didn't even change the distribution. So, this kind of boggles your mind. Well, I don't know if the next slide actually asks a question, so I'm going to ask a question. How can you change a course so as to improve the reasoning skills of students. And I will tell you one thing. The evidence for this, for being able to change courses so that they actually improve students' reasoning skills, has been out since the 70s. And Anton Lawson, the guy who designed the test, actually is one of the exponents for this. So how do you design that? Yes?
Well, it seems like the Chinese learning could have been a lot of memorization, for one thing. And you want to get away from that, and you want them to actually discover this stuff themselves instead of actually just being told or memorizing things. So that's something to avoid.
Okay, that's one answer. Any others? Yep.
Well, the technique of just asking questions and giving the students a chance to sit and think about it on their own, or even the little mini discussions where you can listen to other people's ideas and bounce those against your own.
Yep.
What about if you had to mathematically prove every formula?
Okay.
Like grad school.
Interesting answer. Yes.
That's what my dad uses.
Yep.
Geometry.
Expose students to a very diverse, integrated field of study.
I couldn't.
Expose students to a very diverse field of study, materials that they're not working on.
Okay, something about diversity. I don't think I completely... I would presume, by the way, that the Chinese students actually would be a bit more homogeneous than the American students. You know, because we require everybody to go to school.
Are you saying diverse subjects?
Exactly.
Diverse subjects? Okay, diverse subjects. Yes. Any other thoughts?
I'm not sure how it would work with physics and math, one approach taking culture.
Well, Moore's method, I'm familiar with that. It's a Socratic dialogue method, yeah. And where you don't tell them algorithms, you make them figure out everything for themselves. Okay? Okay. Well, it turns out that Robert Karplus, who was a physicist, and Anton Lawson, who's a biologist and also an expert in cognitive science, came up with what's called the scientific learning cycle, or the learning cycle. They just call it the learning cycle. So in physics, we call it the learning cycle, and everybody goes, well, which one? The learning cycle, because that's the only one we have. Okay. And it basically is exploration, concept development, and application. And one of the things you have to do with the exploration, you don't tell them the results. They have to go and play with, for example, a lever and figure out how it works. And then you have to develop the concept. You give them the terms, maybe you give them some information, you get them to tell each other. And then there has to be some sort of application. It could be physical application, it could be problem solving, it could be all kinds of things. Okay. This is otherwise known as inquiry. And one of the things they did is they took a one-semester inquiry course, subjected students to it, and they found that the thinking score went from 58% up to 66% after one semester. A gain of 0.47 effect size, or 20% normalized gain. 20% is my estimate. Everybody familiar with effect size? Okay. Well, an effect size of 1 means that your curve moved over by 1 standard deviation. It's as simple as that. It's a standard measurement in educationalese. And I think, if you're going to be an educator, you need to have some of these educationalese things. Normalized gain is an invention by Richard Hake, and you can come across his 6,000 student survey on the web. And it's there, you can go and read it. And he invented normalized gain and then found out later that somebody else had invented it ahead of him. But because he invented it in physics, it's now called Hake gain in physics. And basically what you do is you take the amount that the students gained and you divide it by the amount they didn't know at the beginning. So for example, if they scored 25% at the beginning and 50% at the end, they went up by 25 points, right? But they didn't know 75%. So that would be 25 over 75, or a gain of around 33.33%. Very simple idea. And he found that that seemed to be an independent measure of what's going on in the class without being biased by what students came in with. Well, it's not entirely true. if you do a large enough survey, you actually find that there is some bias due to what they came in with. But it's very small. Whereas effect size is a little more nebulous. Alrighty. Recent evidence from math. Jerry Epstein, he's the guy who invited me to the math conference. He invented the concept inventory. Regular courses get 10% gain, interactive engagement get 20%. Again, interactive engagement, you're doing something similar to the Moore's method. Guided inquiry, I'm not too sure whether the Moore's method strictly. All right? And now recently, because people are always saying multimedia. There's some evidence for its effectiveness. And it turns out, there's a recent article that showed something like 20% gain for multimedia if it's designed according to what the cognitive researchers have found out. And they do have intensive investigations of multimedia. By the way, they don't have intensive investigations of books. But they do for multimedia. And I'll tell you my opinion of books. I think most of them are dreadfully designed from the point of view of cognitive research. But they always put them together in a traditional fashion. Okay. So, one of the things they did, a guy in Australia did, and I found this very interesting, and it turns out it's something that could probably be done fairly cheaply for improving results in public schools. Instead of giving kids something to read, what they did was they gave them a multimedia presentation, which is basically a lecture. It's the usual sort of thing. And if you give them just the multimedia where it explains the concepts, the person comes out and explains and shows the demos, and even tells them the answers on the evaluation test, and then you give them the evaluation test, you find out they still don't know the answers, even though they've been told the answers. So is there something you can add to that? We're not going to change it. We're just going to add something to it to improve its effectiveness. Anybody have any ideas? Demonstrate the skills? Well, in this case, what I'm asking is, what can you add to the presentation? Obviously, when interactive engagement, that's the sort of thing where you get the students to do the work. They do it, and you are there to help guide them. It's guided inquiry, generally. You do things, they do this, Dickinson College, for example, they give them this book with all these activities, and they go through the activities, and they learn by going through the activities. They have some lectures, but the point is that this produces very high gain. Okay? But I'm talking about what can you do that would be sort of simple to add to a multimedia presentation that might enhance its effectiveness, something where they're just presenting the ideas, telling them, doing a demonstration. You may not have, you're handing it to them almost like a textbook, something they can study in their own. Yes?
You could have them work together in groups in discussion.
Okay, you could, but of course maybe they're watching this at home. Yeah?
Animations are really good. Nowadays you can program things that move around on the screen.
Okay. I know that's actually being done. Yeah?
Those questions to consider.
Well, what can we add to the multimedia presentation to make it more effective? We're not going to have them do a lab.
No, actually, I'm getting to the question. I'm just posing my thought.
Yeah.
How about adding colors and sound effects?
Oh, you could add colors and sound effects. That's something you could certainly add. I think most of them already have that, but yeah.
Could you make the demos more personal? Instead of having 2 blocks on a beam, you have 2 different sized people on something else that makes it more personalized?
You could, yes. Okay. Any other?
Repetition.
Repetition?
Leave that subject and then come back to it later several times.
Okay, well, so in other words, you have to have multiple multimedia, right?
Right.
Okay.
What about some interaction? Or they could...
That's a possibility, but in this case they didn't have interaction. It was simply a passive watching of it. And yeah,
I think he's thinking like build a video game into it somehow.
Build a video game into it. Yeah, okay. Oh, that would certainly have an effect. I'm not quite sure what it would be. Okay. Okay. So what they did is they found if you just gave them the multimedia, they got 6 out of 24 right. And presuming that was a multiple choice test, it's probably not very good. It's probably close to being a chance. But if they added to the end of it a segment where they had 2 peers, 2 students, discussing the misconceptions involved in the concepts. Literally discussing examples of the misconceptions. Notice there are two things that are important here. One is they deliberately brought up the misconceptions. Two, it was peers. Really important. Peers. It went up to 12 out of 24, 30% normalized gain. And they didn't do anything special. There was no interactivity. But one of the things the students commented on in evaluation, they had to fill out an evaluation, is that they found that they were thinking harder. Well, of course, that thinking hard is good, but sometimes it's unproductive thinking harder. But it did have an effect. Now, people did mention colors and animation and all that sort of stuff. I was going to have something on this, and I left it out, but I'll talk about it a little bit. Okay, Eric Mazur went through some of the illustrations in books and found a number that were, I would say, pretty bad. I mean, just outrageously bad. For example, he showed one where the illustration showed a demonstration of somebody dropping a ball, and as they walked, the ball dropped about a third of the leg or so in each step, which could only happen if you were in microgravity. And okay, sure. So you can always criticize fine demonstrations like that, but then you got interested in finding out whether or not students were actually paying attention to what was in the illustrations. And a lot of the illustrations have a lot of detail in them. They now put, people and trees and stuff. So he put the students into a lab where they looked through a little machine and it followed their eye movements. And so they saw the trajectory of a ball, and the ball. Presumably that's one of the things you're supposed to look at is the fact that it's a parabola, right? And might even draw the attention to that. Well, what did students look at? The most important, the thing they looked at all the time were people. So if you put a person into the diagram, it may completely sabotage it. Colors, it turns out, can be distracting. And he also brought up the point that there are two different, and I didn't know this, although it seems reasonable, there are actually two different systems in your brain for processing information from your eyes. And one processes color, and the other processes black and white. And when you see things in black and white, the black and white portion processes motion. And the color part processes static things. And you can produce great confusion by having motion with bright colors, because what will happen is the color and the black and white, in fact, you can actually put in completely different clues in black and white and color, and depending upon the person's vision, they may see completely different things. So what you put into these textbooks and what you show students needs to be designed to actually get the point across. And my favorite book has nothing but black and white illustrations, line drawings, very simple, very much to the point. The average textbook is not doing that. Therefore, the average textbook is going to be very counterproductive to having students learn. Also notice the average textbook doesn't use a learning cycle. They always give definition and here are the examples. Well, Lawson did a test where he reversed that. He gave them the examples first and the definition last, and it turns out they got 20% better understanding just from reading the passage. Same words. I mean, the examples were the same, the definitions were the same, we just moved them to the end and after the examples. Learning cycle. Very simple things can be done. But it requires, all of this I think requires understanding that a lot of what you assume is not true. It's like learning physics. When you see one car colliding to the other, the average person in the street will say, oh, the big heavy Cadillac pushed much more on the small Toyota, so the small Toyota was creamed. Of course, they aren't considering Newton's second law. Newton's second law tells you that the smaller object will have more of a reaction. And when they're told Newton's third law that the forces are the same, they simply don't believe it. Because it's built in to not believe it. And you have to do all kinds of things to try to get them to believe it. And doing a simple reading, whatever, doesn't work. And so that's what I'm hoping you come out with this is maybe a little discomfort that maybe some of your assumptions about education and how things work are not quite correct. And maybe one or two of you will go and look at some of the literature and dive into it and really begin to learn. Because I can't give you the depth of stuff that's in there. It's been going on since the 1970s. The Shea and 80, when they did an experiment, they showed that you could raise students' thinking by using the learning cycle. And they have something like 30 lessons to be delivered in middle school that literally raise the students' thinking. And at the end of 4 years later, they come out better on English, math, and science. It affects 3 different subjects. Okay? That's been out since 1992. Okay? Feuerstein in 1980 showed that you could do things that would raise people something like 30% on IQ tests. Why isn't that being done? 1980. Then you go back to the learning cycle, which is Karplus, and that was in the 70s. And Lawson is still pushing it. Why isn't that being done?
Well, it seems like there's a tremendous inertia in any institutional system,
Yes.
including the institution of teaching.
Oh, yes.
And I tend to probably, whether I'm conscious of it or not, I suspect I do, model a lot of my teaching techniques on the way I was taught when I went to school, because that's what I know how to do. That's what I learned how to do.
Yeah, and that's what everybody does. Yeah.
I think it takes more planning to do it.
What?
I think it takes more planning on it. You have to get the right thing.
Well, it does initially, because planning a lecture takes a lot of planning, right? You've got to lay it out. I'm one of the ones who plans a lecture, and a lot of times I end up saying things that were completely not in the lecture, depending upon what's going on. And so, for example, you brought up the idea of color, so immediately I thought, well, I'm going to throw that in. The color is not necessarily what you want. But once you get into inquiry, what happens is you don't plan out things in detail. You do plan out the activities in detail, but then what you do is you then have to react. And it's mentally very engaging. I mean, at the end of the day, you come away drained because you have been trying to get inside the students' heads, trying to ask them questions. I mean, the amount of mental activity involved in doing it is much greater than a lecture. Yeah.
I just thought of something. Today I was talking to one of my colleagues who, he's an expert in distance learning. And that's basically what he studies. And right now I'm teaching a class between UH and UHCL where I'm using video conferencing to teach the class. And when I'm doing the video conferencing, basically I'm speaking into the microphone and I have the notes on the screen and I'm walking through the notes and I'm presenting it to the students. And the guy was asking me, so can they see you when you're talking? And I said, well, no, I usually just turn the camera off. And I said, why don't they want to see it? I was like, they don't want to see me. And I realized that, from what you said, it's just extra distraction.
It can be.
If,
it can be.
because instead of them seeing the notes and focusing on the equations or whatever, they could be looking at me.
Yeah. One of the things, again, I'm studying this stuff and looking at it and reading about it and communicating with people and finding out things. And one of the things in multimedia, which I found very interesting, is apparently if you have pictures by themselves, that's okay. If you have words by the people telling you, that's okay. But it turns out the audio plus the video actually work together and you get better results. But don't add in text. If you add text on top of that, the results go down.
It's one too many things.
Yeah.
Overload.
Yes, you get overload. You get overload. The average textbook has overload on every single page. I've gone through many textbooks and I've looked and they've shown 5, 6, 7, 8 concepts. Throw them out on that one page. Now we can do this. We can read this stuff. We can understand. Go, yeah. We chunk it. We can look at it. We can see where it's going. The student can't do that. You only can remember how many things in temporary storage. How many? 5 is a low number, yeah.
7.
7 is about, I think it's from 5 to 9, somewhere in that range. Sure. And the point is the students don't chunk it. They don't look at it and then have that connected to somewhere a chunk down that they can always bring up the details. See, each one of these things is a new item. And when they get to the end of the page, where the result pops out, don't have a clue. They just simply don't have a clue. The book I use, as I say, called Minds on Physics. Even if you wouldn't use the book, it's a great thing to look at because, and it's actually a series of 6 books. It's research-based, and they hit the student with one idea and then try to get them to work them through that one idea. Whole series. My favorite is the one where they show them all kinds of situations and ask, is the normal force, which one has the greatest normal force, which one has the least normal force? And they show them a whole variety of situations. A block sitting on a table, a big block sitting on a table, okay? A block sitting on a table with a spring pushing down on the top of the block. Or a block sitting on a table in an evacuated jar. That's an interesting one. What would the normal force be for you have 2 identical blocks, right? One sitting on a table and one sitting in an evacuated jar on the table. Which one has the greatest normal force?
Slightly greater for the evacuated jar.
Yeah.
No air buoyancy.
Right. Right. And this book is one of the few I know that actually, they talk about buoyancy. We talk about it, and so we give them a few examples of buoyancy to get them to think about it. It's another force. And then there's the one where they show the blocks. Most of them are the same size, but a few of them are different sized. As to which one has the greatest gravitational force. And they have to separate all the effects. Some of the blocks are falling, some are just sitting there. Some are sitting up high, some are sitting low, some are hanging from springs, some are hanging from strings. All the ones of the same size, of course, all have the same, and most of them. But they'll say, oh, the one from the string is different. Well, why is it hanging on a string? Why is gravity pulling more on the one on the string than on the one that's just sitting there? Okay, why is the one falling? Why is it pulling more on the one falling than the one that's hanging from a string? And they're all the same size. So they have maybe a couple that are different sizes. So it gets them to think about one idea and to try to separate out the variables and so forth. And most books never do that. Most teachers never think to do that. So some of these ideas are great. You can look through that series. Minds on Physics. Minds on Physics. Bill Leonard, UMass. I don't know whether he's still there. The group is broken up and they've scattered at the 4 corners of the U.S. I have more material, but I don't have to present it. Yes?
I do have a couple of questions based on things you said about color and motion and people distracting. Question number 1, if our processing of color object for static objects and on the black and white for moving objects, how does our brain ever process something like, for example, a leaping tiger, which is colorful and moving?
Well, yeah. I can't answer that question because I haven't looked that much into the cognitive science. As I say, Eric Mazur has a very interesting video where he does this, and of course there are books that actually tell you about this.
And if you're doing trajectories and the people's minds focus on, attention always focus on people in the scene, would it work to have a person doing a dive off a diving board as the trajectory object? Would that get more understanding? Or would
that I can't answer. The problem is that students tend to focus on is very different from what you think. And I will show you I have some very interesting little things here. See if I can get out of this for a second here. Okay. These are something I recently read and got off the web. So I'm going to go to inattentional. Let me see. Okay, now what I'm going to do is I'm going to bring up one of these. First I'll bring up this one. See if we can show you this one. Now I notice there's something changing in it, right? What's changing? Oh yeah. Immediately you spot it, right? Instantly you spot it. No problem. You immediately spot it. You have no problem with spotting it. However, this one here, what's changing in this one?
The reflection.
It took you a while, didn't it? Yeah. What you do is whenever the picture blanks out, you do what a little kid does when you play peekaboo. You look at all the familiar things to see if they're still there. Yeah. And so this is called inattentional blindness. And you wonder why students sometimes don't pay attention. This one is moderately difficult. And please, let's wait a little bit and wait till most people, if you think you see it, you can raise your hand, but I don't want people to blurt out until other people have figured it out. Okay, what is it?
Railing.
Yeah. People can look at the guy's nose and not even notice the railing. Yeah. See, notice again, people always think, okay, well, students, all you need to do is to look and you'll see it. No, they're always looking at the wrong thing. So when I tell them to ignore the wiggles in the graph, they will tell me, oh, the thing accelerates more. I can tell it's accelerating more because there are more wiggles. I said, ignore the wiggles. This one here is the most difficult. And so again, raise your hand when you see it. I think we have a majority. Will somebody tell them? Tell the others?
Dotted line.
Five grid. Sort of those grids flash on temporarily, and I would not agree that that's the most difficult.
Well, it turns out the cognitive scientists found out it was the most difficult. They found out that this was the one when they tested subjects that more people spent a longer time on this one. They just did.
It's too obvious.
But I mean, there's some that are real obvious. Now this one is real obvious. Got milk? Anyone? And the reason for doing this, and what this shows you, and I think I may have it still the slide that talks about this. Current slide. Okay. The title of the paper, I think, says it all. Experience is not something we feel, but something we do. Because when your vision, in a way, works almost like your memory. In your memory, you only just store a few simple things, and then you reconstruct the rest of it. When you see a scene, you basically pick up bits and pieces by looking around, and then you eventually put them all into a coherent whole that you perceive. But what happens is, something can happen in some portion that you're not looking at, and if you're not aware of that, what will happen is you won't see it. So there's a famous one with the gorillas. Anybody done that one? Yeah, where what you do is these people playing basketball, and you're supposed to count how many times they pass the ball from a white person with a white shirt to a person with a white shirt, and you watch it, and you watch it, and you watch it, and they finally, what's the answer? And it's 15 or 16. The answer is completely irrelevant, because then they ask you the final question, did you see the gorilla? What? Well, while you're doing this, a person walks through the middle of the scene in a gorilla suit, and at least half the people, anybody who's concentrating on the ball, completely misses the person in the gorilla suit. Because it's something that's unexpected. And so when students look at things, they're looking at what you want them to look at. They're looking at something else. And so they're not seeing what you're seeing. And so the whole idea of what we're doing is to try to get them to focus in on the things you want them to focus in, to get them to construct the ideas, because you see, you can't take a concept and put it into somebody's head. They have to perceive what's going on, see it as it were, and begin to think about it to where they put the idea together in their own head. They construct it. You can't communicate the concept. They have to put together all kinds of connections in their head. And that's what we're trying to do. And eventually maybe everybody will be doing it. But there's point out is inertia. It's hard to do. It's hard to change. I changed it on my own because I was already minded to do it. And I'm, an anomaly in that sense. Yeah, I admit it. Yeah.
There's another one, experiment that I was shown years ago when we were talking about this paradigm shift in business, and paradigm became a big word. And we were shown playing cards. We were asked to identify them. And just flashed them on the screen, kind of like you've done here, quickly. And they gave us about a quarter of a second, then about a half a second, then about a second, and then finally 2 or 3 seconds. And we said, okay, we got them. We had them all written down. And 2 of the cards were a queen of, a jack of hearts and a queen of hearts, spades. But what they were actually when we got to study the cards, they were actually black hearts. And so he says, all you guys that have ever played with cards didn't get it right. And there was one guy that said, well, I never played cards much, and I could see it. I thought it was kind of funny, that's a black heart. But the rest of us, our minds, did a little work for us and helped us out and said, well, there's no such thing as a black heart, so it's a spade.
Yeah.
And we were absolutely convinced. We were ready to bet money.
Yes.
That reminds me of something. Once upon a time, I was a graduate student at Rice, and at a time when bridge was a very popular college game. And one time, some of the students played. There was a regular group that played at the Rice Memorial Center. One day, one of the students was brought regular at this game, brought in a deck of cards where the clubs and the diamonds were black and the clubs and the spades were red and the hearts and the diamonds were black, and it really threw some people for a loop trying to figure out what to bid and how to describe it.
Yeah, I understand it. Well, I think I've given you lots of food for thought. Yes.
Could you kind of summarize your concept of pictures? I noticed there was one slide in there that said pictures seem to communicate that they were not a good way of giving in a presentation. Did I misread that?
Well, no.
Are pictures dangerous in some way?
No, the problem with pictures is that people think that just because you show you a picture that you understand it, when in reality that doesn't necessarily happen. What does have to happen in physics, and this is again from the research, is that students have to begin to understand things in multiple ways. They have to understand pictures, a pictorial representation. Typically in kinematics this would be a motion map. They have to understand graphs. They have to understand verbal description. The last thing they have to understand is equations, and that is the last, and I would say the least, because if they understand the other methods, they can actually solve most problems by using these other methods. Equations make it so easy to crank out a solution. You can get solutions to all kinds of things, but then there are a lot of things you can't get solutions to, at least with equations from the perspective of the undergraduate. I can throw a problem that's really simple, and you can graph it instantly and get a solution, but the students, maybe 1 out of 100 could actually write the equations, but only after they've written the graph. Pictures are problematic in the sense that a lot of times pictures are also drawn wrong, they have too much detail. They have things in there that are inappropriate. Yeah.
The reason I'm asking is because I started the research for this project in here by looking at the Challenger, Columbia accidents and the charts that were used to present it. And the argument, the charts were said to communicate incorrectly, and the solution was kind of presented as either doing technical reports or, in future thing, pictures as a better way to communicate than slides.
Well, it depends on what you're communicating, but in reality, I think...
That's too much of a blanket statement, then.
Well, there are different representations, and you have to know how to interpret them. Students, for example, don't know how to interpret graphs very well.
Thank you.
There was a seminal experiment by Heather Brazell back in the 70s where she showed that, and she showed that by doing computer labs with a sonic ranger, where the students moved back and forth and observed their motion, that they could actually learn to interpret graphs much better, at least kinematic graphs. And that's the basis for a lot of labs that appear in a lot of the curriculum. Real-time physics, workshop physics, interactive lecture demos, they all use the sonic ranger because it gives you information, you can immediately see it. But you have to make sure the experiments are all set up properly. So that's part of it. If you can emulate some of this stuff without setting up the stuff properly, and of course it won't do anything. Group work only works if you have stuff, if you give them problems that require a group. If it can be solved easily by one person, why bother with the group? And I think that's, again, there's no one solution, it's a combination, it's a whole package, and you've got to start thinking differently. Yeah.
That thing you said about the groups reminds me of in a class I took in business school years ago. There was one exercise where the professor split up the class into two groups, one group of just 3 people and one group of all the rest of the class, and he gave us 4 problems to solve in like 10 minutes or something. And actually the smaller group got a higher score than the larger group.
But, on the other hand, sometimes one person would get even a lower score. Yeah, it's... the 3-person group, by the way, is considered to be the optimal group for a lot of different things. 4 people is usually considered too many. And that's because you always have, one will be a hanger-on. The point is, 2 people is sometimes a problem because you need a tiebreaker. Yeah.
I was thinking that there was the kind of art, we were talking about communicating through graphs, and I think there's some sort of art to making graphs that communicate well what you're trying, the ideas you're trying to get across. Because I've read papers outside my subject in like Science Magazine, for example, in geology, biology, and so forth. I'm a physics person, basically. And I've seen graphs that were absolutely crystal clear, even though I did not have background in that subject, and I really did understand what the authors were trying to convey with those graphs. And I had other graphs that were like mud, like Greek, like what does it? I see all these lines and axes and have no concept what they mean.
Oh yeah, that happens. My big bug about graphs is a lot of the books, they take stock graphs and stick them in there, and they're usually beautifully drawn. I mean, the artistry is just lovely. And then they either have something that's just completely wrong, or they tends to be, most graphs tend to go through 0 at a 45-degree angle, no matter how they're drawn. Artists love to do that, and yet the truth of the matter is, most graphs never do that. And so students always want to put, I think it's one of the reasons why students always want to put graphs through 0. The graph comes back and it's going to hit the axis. No, they want it to go through, they'll deliberately bring it down and make it go through 0, even though the data shows it doesn't go through 0. So, there are all these little things. I mentioned these to people. Of course, you can't tell the textbook companies because they won't pay you any attention. They don't care. They're selling them stuff, so why should they change it? Anyway. Has everybody got something good out of this? It's completely different from what I said last time, I think, isn't it?
Mm-hmm.
Yeah?
This is very different. Any other questions? Okay, let's thank the speaker. And I'll see everybody next week. See everybody next week. See everybody next week. See everybody next week. See everybody.